Polarity going to be the topic of this lesson, and in particular, molecular polarity. We're going to go back and review the trend for electronegativity we learned a couple of chapters ago, and we're going to learn to identify polar bonds versus nonpolar bonds and how to rank which bonds are more polar, so that's going to be mostly review. But then once we identify these polar bonds, we're going to use that to identify when molecules are polar or nonpolar from there. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. Now, in addition to high school and college science prep, we also do MCAT, DAT, and OAT prep as well. You'll find those courses at chadsprep.com. Now, this lesson's part of my new general chemistry playlist. I'm covering an entire year of general chemistry, releasing several lessons a week. So if you want to be notified every time I post a new one, subscribe to the channel, click the bell notification. All right, so quick review. You might recall that fluorine was the most electronegative element on the periodic table, and the closer you get to fluorine, either going up a group or across a period from left to right, the more electronegative the element. And you're supposed to remember that fluorine's number 1 and that oxygen's number 2, and after that, suffice to say, the closer you get to fluorine on the periodic table, the more electronegative an atom is. Now, in identifying polar bonds, we learned a couple of rules. We learned that if you've got two identical atoms bonded together, that's typically going to be nonpolar, or carbon and hydrogen. And we also learned that if typically the difference in electronegativity was less than 0.5, we'd call it a nonpolar bond. But unless you're given the Pauling scale of electronegativities, it's not usually something we make students memorize, so you weren't going to be usually on the hook for that. But you might have to identify polar bonds, and you might have to identify increasing polarity like we did in an example like this. So in this case, if I said which of these four is the most polar bond, you're looking for the largest difference in electronegativity. Now, if you had, the Pauling scale in front of you, and I'll put it up on the board here, so obviously you'd see that carbon has a value of 2.5, and then iodine's at 2.5, bromine at 2.8, chlorine 3.0, and fluorine 4.0. And so the biggest difference in electronegativity would be the carbon-fluorine bond. So, and again, you could, kind of take a look at this and say, well, there's carbon, and iodine's almost essentially the same thing. And then you got bromine, chlorine, and fluorine. And so you're going to get your biggest difference in electronegativity between carbon and fluorine, not carbon and chlorine, not carbon and bromine, and not carbon and iodine, which have almost exactly the same value. And so identifying the most polar bond here would definitely be that carbon-fluorine bond having the biggest difference in electronegativity. Now, identifying polar bonds, though, here is going to be actually just the first step in now talking about identifying molecules that are polar and nonpolar. And suffice it to say this: if a molecule doesn't have any polar bonds, it is a nonpolar molecule. We'll start there. Going from there, though, if a molecule has polar bonds, it may end up being polar, it may end up being nonpolar. It's going to depend. And it's going to depend on what the polar bonds are and how they're oriented around the central atom. And we'll talk about if they cancel, and ultimately what we mean when we say if they cancel, if the net dipole adds up to 0. If the individual bond dipoles are oriented in such a way that adding them up as vectors sums up to 0, and we'd say a 0 dipole moment, then it's going to be a nonpolar molecule. And so you've got to keep in mind what you've now learned about molecular geometry, though, and you can't just rely on what Lewis makes things look like. Let's take a look at a couple of examples here. So we'll start with carbon dioxide here, and the carbon-oxygen bonds are definitely polar. Oxygen is significantly more electronegative than carbon. And so a couple different ways we could represent this. We could write a partial negative charge on the more electronegative oxygen and partial positive charge on the less electronegative carbon. That'd be one way to represent this polar bond. The other way is we often draw in a bond dipole like so. And you start with a plus sign near the partially positive, less electronegative element, and then draw the arrow through towards the more electronegative. And these represent the same reality. This is just another way of showing that the carbon's partially positive, and then the oxygen partially negative. So either way you want to represent this, but this top way is often really convenient for looking at individual bond dipoles and then seeing if they either cancel or if they sum to some value and the molecule ends up being polar. So if we look, though, we've got another bond dipole on this side. And so in this case, you've got the electrons kind of being pulled towards both oxygens here. Now, one thing you should realize here is that Mr. Lewis makes these bond angles look like 180 degrees. And he would be right in this case. And we'll find out Mr. Lewis is not always right, but he is right here. So these auctions are oriented 180 degrees apart, and that's going to be important. So if we've got equal bond dipoles, since they're both carbon-oxygen double bonds, and they point 180 degrees apart, well, if you added those as vectors, they would add up to 0. And so we'd say that this molecule, even though it has individually polar bonds, overall it has no overall dipole, or no dipole moment, we might say. And as a result, we'd say that this molecule is nonpolar. So oftentimes we'll explain this to students in instead of looking at this as the sum of vectors, because that's usually something you'll study in more detail in physics, and a lot of our students haven't had physics yet. We might talk about, pulling a rope on this carbon. And if we pull equally, since these are both auctions, equally in exactly opposite directions, since the bond angles are 180 degrees, the question is, would the carbon go anywhere? It's kind of how we like to phrase this. In this case, it wouldn't. If they're pulling equally in exactly opposite directions, well, then the carbon's not going to be pulled net in any particular direction. And that's one way of getting evidence that the bond dipoles add up to 0 and the overall dipole moment is 0, so the molecule is nonpolar. So if you get a 0 dipole moment, you're nonpolar. If you get a non-zero dipole moment, then you're polar, is generally how this works. And the greater the dipole moment, the more polar the molecule. So if we contrast that with this lovely molecule here, where we replace one of the oxygens in carbon dioxide here with a sulfur, one row down on the periodic table, one period down. So we've still got two polar bonds here, the carbon-oxygen bond. Again, still polar. The carbon-sulfur bond is a little bit polar, but much less than the carbon-oxygen bond. And so I'm going to draw a smaller arrow. And as a result, we still have two bond dipoles that point 180 degrees apart, but they're not equal in magnitude, and so they don't add up to 0 this time. And so overall, we're going to have an overall dipole moment pointing towards the right. And so when you have an overall dipole moment, sometimes they have you draw those in. And in this case, the overall molecular dipole would point to the right, because essentially adding this bond dipole with this one, the one pointing to the right, is more than going to make up for the one pointing to the left and then some. And so the overall molecular dipole is going to point towards the right. And so in this case, both these molecules have polar bonds, but whereas the first one, the individual bond dipoles canceled, it was nonpolar. In the second one, they don't completely cancel. And so we refer to this molecule as being polar. And so we've kind of learned the strategy then for identifying molecules as being polar and nonpolar. And it turns out this is really important, because it turns out this is going to affect the properties of these molecules and things like boiling points and melting points and viscosity and things of the sort that we're going to study later on. So it's actually rather important to the properties of a material whether or not you can identify it as being polar, and in some cases how polar. So, but first thing you want to do then in this strategy is just identify, do you have any polar bonds? If you say no, then no polar bonds means it's going to be a nonpolar molecule. But if you have polar bonds, then you got to look at how they're oriented and their magnitudes and say, do they cancel, i.e. do they add up to a net dipole of 0? If they add up to 0 and cancel, then it's a nonpolar molecule. If they don't perfectly cancel, then it's still going to have some residual polarity and be a polar molecule, as in the second case here. So one thing you got to be careful of is you got to be careful of Mr. Lewis, because he doesn't always tell the truth. So if we take a look at this example here. So here's CH2Cl2, and this molecule is indeed polar, as we're going to find out. But it's really common for students to assign this one as being nonpolar, because they look at this and they're like, oh, let's see, Chad told us, that carbon-hydrogen are the two different atoms that still form a nonpolar bond, and that's true. Turns out carbon is just slightly more electronegative, and technically you'd have a really tiny bond dipole pointing towards the carbon that you can pretty much ignore. But the carbon-chlorine bonds are indeed polar. And so a lot of students look at this and they're like, oh, they're equal in magnitude, they're 180 degrees apart, and so yeah, it's just like CO2 and this is nonpolar. Except the problem is that they're not 180 degrees apart. So carbon here's got 4 electron domains, and with 4 electron domains, you're supposed to know that the electron domain geometry is tetrahedral, and the bond angles are not 180, they're 109.5. And so even though, again, Mr. Lewis makes everything look either 90 degrees or 180 degrees, none of the angles in this molecule are 90 or 180. They're all 109.5. And so if we try to draw a little better three-dimensional representation of this molecule, we can kind of see what's going on. And so here we kind of represent that tetrahedral structure here with 4 electron domains. And you kind of see the bottom of the pyramid right here, and then going up to the chlorine for the top of the pyramid. And if now we draw in those polar bonds again, one here and one here, we can now see that these don't point 180 degrees apart. They're just 109.5 apart, and they're not going to cancel. And in fact, when you add those two together as vectors, you get the average of them, and the average of them would point right down the middle of this molecule. And so the overall molecular dipole moment is what I've diagrammed in blue. It's when you, again, sum up all the individual bond dipoles. And again, if they don't cancel perfectly, then you're going to have some overall molecular dipole that you could potentially draw in, like we've done so. Cool. And so once again, this molecule is indeed polar, but again, drawing the Lewis structure like this, a lot of students would mistakenly identify it as being nonpolar, but no, definitely polar. Don't make this mistake. Now, one thing to note here, if you've noticed in the first example, we had 2 of the same atom around the central atom, and it ended up being nonpolar. Now, sometimes that'll end up being polar, sometimes nonpolar, and we'll see that lone pairs around the central atom are going to be something really important to identify here in a second. But in these last 2 examples, when we had different atoms around the central atom, different atoms around the central atom, usually the case is that's going to end up being polar because your individual bond dipoles are not usually going to cancel. That's another thing to identify. But most of the molecules you're actually going to be asked to identify as being either polar or nonpolar. They're going to have identical atoms all the way around, and we'll have a pattern to recognize for identifying these as polar or nonpolar here that we'll take a look at. So now we'll take a look at some more examples here, and I just want to point out the first 3, and obviously we already did carbon dioxide, but what you're going to notice is that if you've got all of identical atoms around the central atom, and that central atom has no lone pairs, then your bond dipoles will cancel and it will be nonpolar. So, and again, we saw that with carbon dioxide. These really were oriented 180 degrees apart, and the bond dipoles cancel, adding up to 0, again making this nonpolar, having a 0 dipole moment. Now in the case of BCl3, so this guy's trigonal planar, and your bond dipoles here are all oriented 120 degrees apart, and if you pulled on this boron in 3 different directions 120 degrees apart, he'd go nowhere. All these bond dipoles add up to a vector sum of 0, and again he ends up being nonpolar. And again, it's important to recognize that, again, Lewis doesn't always tell the truth, because we commonly would draw the Lewis structure for this guy. So like so, and if you draw the Lewis structure like this, making everything look 90 or 180 apart, and you draw in those individual bond dipoles, you might be like, well, these 2 cancel, but nobody cancels him out. But again, you have to remember that don't go by what Lewis tells you the angles are. You have to know, based on your knowledge of molecular geometry, now what are the real bond angles? What is the real 3-dimensional geometry, or in this case 2-dimensional geometry of this guy look like? Well, he's trigonal planar with 3 electron domains, and these are all 120 degrees apart, not either 90 or 180 apart like Lewis might make you think. And so again, don't just rely on what the Lewis structure looks like. Keep in mind, what does the actual molecular geometry look like when you're trying to figure this out? Same thing here. We'll move on to XeF4 here. In XeF4, we've got 4 electron domains. So therefore, it's going to have an electron domain geometry that is tetrahedral. And with all of them being bonding, that means the molecular geometry is also tetrahedral. And so all these bond angles are 109.5. And again, they're all equal in magnitude since they're all carbon-fluorine bonds, and they're all oriented 109.5 degrees apart, and it turns out they're going to add up to a vector sum of 0. And this one's not so easy necessarily to visualize with it being 3-dimensional and stuff, but trust me, it will add up to 0. And this guy's also nonpolar. And once again, if you have identical atoms all the way around your central atom and no lone pairs on the central atom, it will be a nonpolar molecule, rest assured. That's something you can take to the bank. Now, if I replace a couple of these fluorines with a couple of hydrogens, or even one of these fluorines with a hydrogen, or 3 of the out of the 4 fluorines with 3 hydrogens or something like that, well, then I wouldn't have the same atoms all around, and it wouldn't necessarily have bond dipoles that cancel, then it would end up being polar. But again, for now, we're just going to consider several examples where all the outside atoms are identical. Now let's see what happens when we put lone pairs on the central atom here, and I forgot them off the outside atoms. But in these next 2 examples, the central atom is going to have a lone pair in both of these. Now for the first one here with SO2, so Sulfur here's got 3 electron domains. 2 of them are bonding. It's bonded to 2 atoms and a lone pair. With 3 electron domains, that electron domain geometry is going to be trigonal planar. But with a lone pair on the central atom, the molecular geometry will not have the same name, but in this case will be bent. And so I've drawn the kind of the three-dimensional geometry here. These are not 180 apart. They're closer to 120 apart. And if we draw in those bond dipoles, knowing that they're about 120 apart, well, in this case, since they're not 180, they are equal in magnitude, but since they're not 180 apart, they're not going to cancel perfectly. And this guy is indeed going to be polar. And the average of these two bond dipoles would be a bond dipole pointing right down the middle of that molecule. We'll see something similar here with NF3. And once again, we've got 3 polar bonds, so those NF bonds, and we could draw in those individual bond dipoles. So, but once again, that central atom's got a nitrogen on it. So keep in mind, nitrogen here's got 4 electron domains. So 3 that are bonding and then 1 lone pair of electrons. So that's going to make his electron domain geometry tetrahedral. But again, with the central atom having a lone pair, the molecular geometry will not get the same name. In this case, with 3 bonding domains and 1 lone pair, it's called trigonal pyramidal, you might recall. But the angles here are all roughly 109.5, keep that in mind. And so in this case, if the nitrogen had been surrounded by 4 fluorines like carbon had over here with another one pointing up, they would have canceled. But without the fluorine up top pointing up, these 3 aren't all perfectly going to cancel. In one way, shape, or form, they all are pointing downward. And as a result, right down the middle of this molecule, there's an overall bond dipole, and this molecule is polar. Those bond dipoles don't perfectly cancel. And so, again, here's the deal. Again, assuming you have all identical atoms around the central atom, we've now taught you that if there's no lone pairs on the central atom, it will be nonpolar. All the bond dipoles will cancel. Cool. And now we've shown you 2 examples where there's lone pairs on the central atom, and they both ended up polar. And so students get to thinking that, well, if there's no lone pairs on the central atom, and again, assuming all identical atoms all the way around, it's going to be nonpolar. And if there's lone pairs on the central atom, it's going to be polar. And most of the time, that would be correct. So, but you got to be a little careful. So let's look at one more here with water that you're commonly going to see. And again, it's another one that's a little bit tricky because the Lewis structure is often drawn like so. And if you just go by what Mr. Lewis says, these look like they're 180 degrees apart, and they're not. They're, again, a little less than 109.5 degrees apart, we learned. And as a result, not according to what Mr. Lewis shows, but what we know about the real molecular geometry, these don't cancel. And as a result, there's going to be an overall molecular dipole. That's the average of those 2. And this molecule is indeed polar. In fact, water is known to be really polar. Cool, so yet another example where the central atom had lone pairs and it was polar. And most of the time that's going to be the case, but I do want to show you a couple of exceptions. All right, here's the 2 examples we're going to look at here. Notice there are indeed lone pairs of electrons on the central atom in both cases. In this first one here, count up your total number of electron domains here, and we've got 6, 4 that are bonding, and then 2 non-bonding domains for a total of 6, so the electron domain geometry is octahedral. But with the central atom having lone pairs, the molecular geometry will not go by that same name. And when you've got 4 bonding domains and 2 lone pairs, so that is going to be square planar. So with square planar, you've got a certain degree of symmetry here. So, but these really do form a perfect square. And so if you look at this polar bond, it's going to cancel perfectly with this polar bond because they really are 180 apart in this square planar structure. Same thing with this one and this one. They're really 180 degrees apart when it's a square planar structure, and their bond dipoles are going to cancel. And so all 4 bond dipoles add up to 0. And so as a result, this molecule is nonpolar. And a lot of students will get this wrong because like, oh, Chad has got lone pairs. And again, the rule is not that if you have lone pairs, you're polar. The rule is if you don't have lone pairs, you're nonpolar. But if you have lone pairs on the central atom, it's probably polar, but here's your first exception. With the square planar molecular geometry, it has a chance of being nonpolar, assuming, again, not just a chance, it will be nonpolar if the outside atoms are all identical, in this case, all fluorines in this example. Cool, we'll look at another one here. Here we've got 5 electron domains, 2 bonding, 3 non-bonding. 5 electron domains means trigonal bipyramidal electron domain geometry. And once again, because the central atom has lone pairs, the molecular geometry goes by a different name. And in this case, with 5 total domains, 2 bonding, 3 non-bonding, it is going to be a molecular geometry called linear. And that's important because being linear in a straight line, it means that these two xenon-fluorine bonds are 180 degrees apart. And so their bond dipoles are equal in magnitude and exactly 180 degrees apart, opposite in direction, and add up to 0, meaning this is once again going to be nonpolar. But it turns out this is it. So the linear molecular geometry with 5 total electron domains, or the square planar molecular geometry with 6 total domains, they are the 2 examples where you can have lone pairs on the central atom but still be nonpolar. But all the rest of those geometries that have lone pairs on the central atom are typically going to end up polar. So like bent or trigonal pyramidal, or the other version of bent with 4 electron domains. With 5 electron domains, you could be looking at like the seesaw or sawhorse. That's typically going to be polar. What else we got there? We got the T-shaped. That's definitely going to be polar as well. And then with 6 electron domains, you've got the square pyramidal, and that's typically going to be polar as well. All the bond dipoles don't cancel. But again, the 2 examples with lone pairs on the central atom that still have a chance of being nonpolar, and typically are, the square planar or the linear variant where it's got 5 total electron domains. So just want to make sure you have seen that once before, because again, these 2 examples in particular are the ones that commonly show up in the test because professors expect you to have a better chance of getting them wrong. Now, if you found this lesson helpful, would you consider hitting that like button? Really helps to support the channel and lets YouTube know they should be sharing this lesson with other students as well. And if you'd rather not hit that like button, then my request of you is that you smile at a stranger in the next 24 hours. I know, spread that kindness. If you're looking for general chemistry practice, check out my general chemistry master course. Over 1,200 questions, so quizzes, chapter tests, practice final exams. There are also final exam rapid reviews, and all the study guides come with it as well. A free trial is available. I'll leave a link in the description. Happy studying.